Okay, welcome. Thank you for coming. So, just before I begin this new chapter, I just want to say a few more words about when we finished last time. I want to clarify a few points. So so when I was talking about self energy, let me redo this. So here we have the 1 over minus omega plus I eta square plus omega 0 square. And then there's some damping. So just to simplify the notation, and here I will drop the mass and everything. Let me write here some object. I don't know, pi. Let's see. So the point is that if I do a perturbation theory in powers of the coupling between the bat and the particle, then I will get a power series that will be that if I do a power series for this, that will be 1 over minus omega plus I eta square plus omega 0 square. Then if I expand here to first order, then I have minus pi over minus omega square plus I eta plus omega 0 square plus etc. But now what I've done is just expand directly this, which is the answer I know. But if I'm just doing a power series in some coupling between the bat and the oscillator, I will get this that I will call D0, and I get some term that's of order of the square of the coupling, k prime square times D0 square. K prime times some mess. Let me call it anything. So P for perturbation times D0 square, and again some higher order term K double prime 4 times something to the some other thing that's of order 4 times D0 cube plus etc. So this term that is let's say second order, here I assume that the power series is even in the coupling constant. So this term that's of order coupling constant square comes from this, and this K double prime 4 comes from this also, but this also has a power series. So you see that it's better to take, for example, the second order term in the power series of this, and to rewrite the result like this, instead of working directly with the power series like this. And the reason is that we know that the poles are related to, I mean that the structure of this function is like this. So we that's the reason we want to do it like this. This will have terms of order. This by itself will be k prime square, k prime 4, etc. So the power series itself will mix all these terms. And you see here I have the pole of this, then I have the pole square, the pole cube, etc. What I want here is the pole that is just shifted by this object. So that's the first remark I want to do. Are there any questions on this? Then the other remark is that if I go back to this form about virtual particles, so I had 1 over minus omega plus I eta square plus omega 0 square. Then let me go back to the form minus I omega gamma of omega. Now you see this object can be, I can write the real part of this obeys the Cramer's Koenig. So it has minus p integral minus infinity to infinity d omega prime over pi of gamma double prime of omega prime divided by omega prime minus omega. Now I showed you that this has a lots of poles, and so suppose that gamma double prime I wanted to write it backwards. Sorry, this way. I have the minus sign here. So this is the imaginary part that's related to the real part. So the real part, the thing that's related to absorption, the absorption will occur in some frequency range. Whoops. It should be an even function. So I write it like this. So suppose that I'm looking now at oscillations in this frequency range. Okay, I'm interested here. So outside the region where gamma prime is different from 0. So in this region, there's no absorption for that frequency. So gamma prime at that frequency is 0. So for that frequency, it means that I can write here. But you see, gamma double prime will not be equal to 0 because it obeys this. So even if gamma prime is 0 here, it's non-zero elsewhere. So here I have I omega, and then I have some imaginary part here, so that I write in the form I gamma double prime of omega. So you see, in that regime, the oscillator is not damped because at that frequency, the oscillator is not damped, right? So all that happens is that the oscillation frequency is renormalized, it is changed. So I still have a harmonic oscillator with a renormalized frequency, which means that I can think of having a phonon, an excitation, a particle that makes transitions. But this particle contains, in some sense, the effect of all these other eigenmodes that were in the bat. And these eigenmodes that were in the bat, I can think of them also as particles because, again, they would be quantized. So these particles that are in the bat that influence me now, they are called virtual particles because they don't lead to any dissipation. Okay? I'm not giving any energy to these particles. I mean, I'm not giving all the energy, if you want, remains in the oscillator because there's no damping. But the frequency of that oscillator is influenced by the presence of these other particles that I call virtual particles because they are not, I mean, there's all sorts of jargon associated with that. Sometimes we say they're not on the mass shell or something like that. I mean, they don't lead to any absorption. Is that okay?
Yeah, it's pretty clear now. Thanks.
Okay. So Now today I want to step back a little bit, and we start the real topic in some sense. We go to the quantum mechanics. And for any physical theory, what's important is what is measured, right? I mean, you need to first specify what you measure and then have some mathematical formalism to describe this. Well, in quantum mechanics, we know that if we know the wave function, we can compute any observable. But you understand that the wave function is a very complicated object, right? Because it is, I discussed that at the beginning. So there are certain cases where you can work directly with the wave function. For example, if you can use variational approaches, and we will see that the BCS theory, for example, has a variational wave function. There's also the fractional quantum Hall effect that has also has a variational wave function. But in general, it's quite difficult to work with the whole wave function. Modern methods like density matrix renormalization group or tensor networks, they have made wave function methods popular again, because with powerful computers we can work with the full wave function. But in many cases, these are also variational wave function in some sense. So another way to go around the wave function is to use Feynman diagrams, which as I said, is just using perturbation theory and expressing the results with diagrams. So what we prefer here is to focus on observables. Don't try to get the whole wave function, but try to get some reasonable approximation for the wave function. So what I will show today is that there's this link to experiments, and I will tell you that in many body physics, so the physics of many particle systems, quantum materials, or condensed matter physics, if you want, the observables are of two types. One is more like scattering. You come with a neutron and you scatter, or you come with a photon and then an electron comes out. Or you come with light. You come some infrared light and there's some absorption. Or you come with a photon, a red photon and a blue photon comes out. So that's Raman scattering. There's a nuclear magnetic resonance. So there are a number of probes that are like that, and these are all scattering probes. So the result of measurements in that case are correlation functions, or if you want, these type of experiments measure fluctuations. Another type of experiment like conductivity, electrical conductivity, thermal conductivity, Seebeck effect, all of these transport quantities, they measure linear response. And so they give transport quantities, and they're also expressed in terms of correlation functions. So in this section here, we want to see what we measure, and I will show you this. That with these scattering experiments, what we measure is fluctuations. This will be based on the golden rule. And in the case of conductivity and transport quantities in general, it will be linear response. So and that linear response will also be a type of correlation function. But before I go to linear response, I need to do time-dependent perturbation theory here. Here I don't need it, but here I will do that. So next time we'll see a little bit more. So this expressing the results in terms of correlation function has the advantage that we can also do some, once we have the general formula, can also do some approximation. You see in the harmonic oscillator case, for example, I know that the damping constant, sometimes I can approximate by a constant. So in this chapter, I will also discuss general properties of correlation functions. But I've already done that, or in some sense, with the classical harmonic oscillator. So Kramers-Kronig relation, for example, I've already discussed, and the positivity of what is implied by positivity of dissipation, etc. So these I won't need to go into much detail, but there will still be some things like some rules that I have not discussed yet, which are exact results of quantum mechanics. Also in classical mechanics, actually, there are some rules. And so these put constraints on correlation functions also. So is the program clear? So I just give you, let's start with this link to experiment where we talk about scattering experiments. So an example is that I come in with an electron, and the electron is scattered. And if I look at the cross section, d square sigma d epsilon, the final of the electron, d omega final, where omega is the solid angle here. This turns out to be equal to m square over 2 pi cube h bar 5 times the square of the Coulomb, the Fourier transform of the Coulomb interaction, VQ square, where Q is the momentum transfer. If you think of this as an incident wave vector, Ki, and this as a final wave vector, Kf, then Q is Kf minus Ki. So Kf and Ki come here. Kf, Ki, and then I have the integral dt of e to the I omega t times rho of t rho of 0, where rho is the density of electrons in the system. So inelastic electron scattering like this measures a correlation function, the density correlation function in that system. And omega is the energy transfer. So Q is the momentum transfer, omega is the energy transfer. Now you see this piece here in front refers only to the external probe. And I know everything about this, right? I know Kf, I know Ki, I know all this. And this is what I'm measuring. And I'm measuring what's happening in the material here. I'm measuring the density correlation function. So the reason it works so well is because we will always be talking about weak probes, in the sense that the golden rule Fermi's golden rule can be applied, and Born approximation. In other words, this comes in a pure plane wave and comes out as a plane wave. So, as I said, neutron scattering, all the probes will have this property. So this I will not derive, but I just want you to see the structure. Okay, deriving it will take me a lot of time. What I will show you is more a sketchy proof. I mean, of using the golden rule, a proof that is quite general. So is it okay? Can I go now? Okay. So the golden rule tells me that the probability of going from some initial state to some final state is just equal to 2 pi over h bar times the square of the transition matrix element from the going from the initial to the final state times delta of final energy minus initial energy minus h bar omega. So what I mean by all these energies, so I have energy conservation, so that the final energy, so this is the energy of the system that I'm probing, plus epsilon f. Epsilon f is the energy of the is the final energy of the probe. Okay, that's the system, that's the probe, and that's equal to the energy of the system at the beginning plus the energy of the probe at the beginning. Okay, so total energy is conserved. So EF minus EI is equal to epsilon I minus epsilon F. And this is what I call h bar omega. Okay, so that's the conservation of energy. So now the Hamiltonian that I write will, I take a general form. H will be H system plus H probe plus some interaction between the probe and the system. And I write that very generally. So I write that the interaction between the probe and the system is some coupling constant G times some operator that refers to coordinates of the probe and another operator that refers to coordinates of the system. So you can think of this as the electron coming in, and the system is being measured there. Well, P and S have some arbitrary significance in some way, so we will see different cases. But there are two systems, okay, P and S. And we assume that we know everything about P, like here, about the probe. And the system is what we want to know about. Okay. So what I need now is to compute this matrix element. So VFI, okay. And I assume that the final state, the probe is far, okay? So I write P final, and the system is in some final state that I call SF. And now this is the what makes the transition. So I have G AP AS times S times, I'm sorry, P times P initial times S initial. So everyone is familiar with this notation. It just means that I'm juxtaposing the things, and here I should have also written a tensor product like this. So AS acts on this and AP acts on that. So very simply, this is just PF AF PI times SF not F, AP, a probe, a system, times the initial state times the coupling constant G that was there. Okay, so I'm looking at the beginning, the probe and the system are separated, and at the end, the probe and the system are separated. So I can just take a tensor product of the two states. Okay, so now I just need to put this back in that equation. And it becomes, so I will put this square. So there is G over H bar times PF AP times PI square times same thing for the system, SI A system, SF, excuse me, S initial square.
Just to be sure, when you wrote the density above the correlation of the density at time t and 0, you meant by that the density of whatever is interacting with the light?
Here I'm sorry, I should have mentioned, here it's an electron, so it's a Coulomb interaction. So that's the charge density in the system. Good
Oh, okay.
question. Okay?
Okay, yeah.
I was not very clear in explaining this. So, and then I have 2 pi times delta of EF minus EI minus H bar omega. I'm confused with my H bars here, so let me put it back the way it was. Okay. So so now I put it in the form. It's starting to look like this in the sense that this refers to the external probe, and I assume I know all of this. And this looks like what's happening in the system, but it's still not this form here. So the way we will make the connection is using the Eisenberg equations of motion. So you know that, right? So it's the Eisenberg equations of motion and a trick that's due to Van Hove, I think, which is to use the direct representation of the delta function. So this delta function I can replace by the integral dt of e to the I omega t times the exponential of ei I times ei minus ef times t over h bar. Okay, so if I integrate from minus infinity to infinity dt, that would give me a delta function of omega plus ei minus ef. But here I add an h bar, and here I put some h bar, and I know that the delta function of anything omega times h bar is equal to 1 over h bar times delta of omega. Okay. So here, here I need to, well, where do I put the h bar? I think I put the h bar there.
I'm not sure that you should put it there, since you divided in one of the exponential by h bar, and you were supposed to have h bar
Oh, yes.
right next to the omega. So when you, yeah.
Yeah, so it should be in the numerator, right?
Yeah, just because you put it in the exponential.
Yeah. So this would be, so this is delta, so this is delta of omega minus ei minus ef over h bar. And so this is, so if I factor 1 over h bar and take 1 over an h bar, then it means it is h bar delta of everything. So it means that so this would be the, so I need h bar square here, right?
It's not the line right below that you should put the, no, in the notes it is,
Yeah,
in the notes, the h bar on the line above is on the numerator at power 1.
Okay, yeah, it's power 1, but I have h bar square here, right? In the notes, I think I have some h bar here.
Ouais, exactement, oui.
Oh, yeah.
Yeah. Okay. So, so the point now is that if I do this this replacement, then I can do this. Here I can use that S final times e to the I h t over h bar times a s times e to the minus I h t over h bar s I is equal to sf times the exponential of I eft over h bar. So now I'm assuming that this is an eigenstate of energy. Okay, times as times e to the minus e I t over h bar times si. So now you see that instead of having this here, I can put it inside. So it means that now I can rewrite this like this. Okay, G over H bar, PF, AP, PI square. And now I'm going to write SF E to the okay. Times SF E to, okay, sorry, I'll get it straight. E to the
say SE.
SEM. I should here I put it this way, right? SI E to the IHT over H bar, AS E to the minus IHT over H bar, SF. Times SF A S S I. And now I have to do some integral e to the I omega t dt. Okay, so I've used this the direct representation of this delta function. Now you see that this is the before I go any further, we are not measuring the final state of the system, right? We are just measuring the final state of the probe. So it means that the only thing that makes sense to compute is the sum over the S final. Okay.
What you mean by that is that the S final is the states that correspond to the measure we did?
Yeah, S final is once the probe has come out, the system is left in some state.
Yeah.
That I call SF.
Yeah, but we don't know what this state is.
Yeah, exactly. You don't know what the state is. And so there are many states that can lead to the same exit state from a probe.
Yeah, okay.
Okay, as long as they conserve energy. And momentum will be conserved through the matrix element. That's something.
So are we considering?
Okay.
Yeah, we
Yes.
are considering the time evolution as well, right?
Pardon me?
We are considering the time evolution there.
Yes.
Okay.
I just rewrote the delta function with the direct representation of the delta function. And then I use the fact that I can go to the Eisenberg picture that I have not discussed yet in detail. But you should be familiar with these Eisenberg equations of motion. Now
Okay.
when H acts on SI, it gives me EI, and when here it gives me EF. So in the end, with this I omega t here, I have this delta function. Okay. So you see what happens if I sum over SF. I can use the closure relation, okay, the completeness relation, and I can erase this completely. Okay. So what is this now? This is just the Fourier transform of a correlation function in the system. Okay, you see it has this structure now. Well, I forgot the AS here. So this is the time-dependent quantity, so I can call it A of t, AS of t in the Eisenberg picture. Times AS times SI, and I take Fourier transform. Okay. So it has this shape here. So this is this, and this is this guy. I have integral dt ei omega t integral si as. Okay, now one more step. In general, the system we're looking at is in thermal equilibrium. Okay. So if the system is in thermal equilibrium, I don't know exactly what is the initial state. It's not the ground state. So I have to average over all possible initial state, consistent with the fact that I know that the system is in thermal equilibrium. So what I want to do here is to compute the sum over all initial state, e to the minus beta times energy of the initial state. I can even go to canonical ensemble and grand canonical and write it like this, times the sum over final state of P of IF divided by sum over I of e to the minus beta ei minus mu n. You are with me? Okay. This is just a grand canonical average of this. So in other words, I have to put here e to the minus beta h minus mu n. Then I have to sum over these SI. And I have to divide by the partition function, the grand partition function. Z, I think we will call it big omega here, or exponential of big omega. But anyway, some partition function. And I have to sum over all these. I'm sort of dying for space here. I have A of t s, and I have sum over I of I e to the minus beta h minus mu n. Okay, and I'm summing. So this is a sum over I of si. So this is right. So normally what we do is, because you see H acting on SI will give me this EI.
Just to be sure, right now we are summing over all these states that make sense to be in equilibrium and that preserve energy. But I could imagine a system that is in a very special state. I don't know what it is, and it stays in this special state or around this special state. And when I interact with it with a probe, it stays in this special state. It does not go, or it stays around the special state without going to the other equilibrium state that we are summing over right now. So for all I know, the averaging that we're doing now could, well,
What
not
we are
necessarily.
averaging is only over the initial state. We're summing over all final states here.
Mm-hmm.
But we have to average over all possible initial state weighted by the we're doing a thermal average, and I cannot do anything else really if I'm thermal equilibrium. Okay, before I send the probe, I let my system come to equilibrium.
Mm-hmm.
And then I look, there's an electron that comes out, there's some scattering. And then, when I do the experiment, I don't send just one electron. I send a beam of electron and I detect a beam of electron. And what I will get is some result that is sort of an average over the thermal ensemble. Another way to look at it is that this thermal equilibrium thing selects the states that basically have very similar values. For example, observable values. For example, think of a spin system. So in the Ising system, you have 2 to the n state if you have n, 2 to the n states if you have n spins, right? So this is exponentially large. But the magnetization, if I have an n spin, can take only 2n values, minus 2n to 2n. So most of these exponentially large states have value of magnetization that don't vary that widely. And what this does basically is to select a subset of states that have this typical value that is appropriate for that temperature.
Just to share with the class, the idea that I had is that I thought, well, we could be in a system that has a special state that it will stay in or around that special state. And for all I know, the averaging that I'm doing now could be inducing some error because I shouldn't consider those other special states.
Yeah.
But assuming that we know what the energy of my state can be in, then it still should be okay if I understood your answer correctly.
Yes. What I'm saying is that the state will certainly go to some final state because the probe is doing something, right? I mean, it's perturbing the system. It cannot stay in the same state. But we sum over all final states, and we saw that we can use a complete set. But we don't know the initial state. But we know it's in thermal equilibrium. So we do our best. We average over all possible states weighted by the density matrix or this Boltzmann factor. So what we get is a thermal average. It's not perfect. We don't know what is the initial state of the system. We will never know. But we know that it should be a typical state that is consistent with thermal equilibrium. That's the only information we have. You could prepare, let's say, the state in some very special state that you know because you're doing some quantum computing of some sort. Then you should not do this. You just take the states you're doing. Okay. But if all we know is that the system is in thermal equilibrium, then we average like this. So this operator, exponential of minus beta h minus mu n divided by z, is called the density matrix usually. Okay. And what I mean by these brackets here is exactly this. In other words, I mean, take a thermal average and a quantum mechanical average. So you take a quantum mechanical average, initial state, and you weigh this with the this quantity. So another way to write exactly this is perhaps I should have just written it below. I'm sorry. Now that I started to erase, there's no way to go back. No time reversal symmetry with erasing. Okay, so so here I have I'm compute. Let me take the integral e to the I omega t d a little bit closer to us, and then I can write a trace of e to the minus beta h minus mu n times a system of t, a system divided by z. dt. So that's another way to write this. And when from now on until the end of the class, when I write these brackets, I always mean this. So the trace here is the quantum mechanical trace over states, and this is the density matrix. So this is a thermal average.
So density matrix is the diagonal one?
The density matrix is e to the minus beta h minus mu n divided by z. So it is diagonal in the energy eigenbasis.
Okay.
But it's not diagonal in general. If I take matrix elements between the state A and state B, I may get something that's different from zero for general states
but
A and B. So it has off-diagonal elements.
But the trace.
Excuse me?
But the trace is basically the summing over the diagonal elements.
Yes,
right?
exactly. That's what the trace means.
Okay.
So if A and B are energy eigenstates, then the density matrix is diagonal.
Okay.
Because H acts on this and it gives energy. And now, so it's an eigenstate. So, and now this is an energy eigenstate. That's another one. They will be orthogonal. So, so the density matrix in general is not diagonal, but in the energy basis, it is diagonal. Okay, so I just want to make a few remarks before we finish. So this is just something funny here or interesting. Okay, suppose here that the probe here is just some I'm just looking at some atom in the vacuum that is decaying. Okay, it's spontaneous emission. So the atom is in the initial state is some excited state, and the final state is the atom in the ground state. So here I have the expectation value of a system of T, a system. And so this average here means what I just explained. Okay, now an atom that decays, what makes it decay? I will show this later, but if you've done a little bit of quantum mechanics, you know that the coupling between matter, so AP, the coupling between matter and electromagnetic field is the dot product of the current operator times the vector potential, G dot A, okay? So my H that went from probe to system. So here the probe is the atom that is decaying, and the system is the vacuum of the electromagnetic field. So what causes the transition are if I'm at zero temperature, what is causing the transition here are the 0 point fluctuations of the vacuum. Okay. If I'm doing a nuclear magnetic resonance experiment, what am I doing in nuclear magnetic resonance? I take a spin, with a magnetic field, I put it up, and then I look at how it decays to this equilibrium position. So this is the spin is doing a transition from up to some final state that is, let's say, down. So in that case, we have the nuclear spin is coupled to the environment through, for example, the hyperfine interaction. So that's the spin of the surrounding electrons, for example. So here, this would be the spin-spin correlation function. So in nuclear magnetic resonance, if you look at this free decay of the spin, what you're measuring are the spin fluctuations in the system. So the probe is the nuclear spin, and the system is the electronic spin that are around. So you're measuring the fluctuations of the spin. And in the case of an atom that's decaying, you're measuring, as I was saying, the vacuum fluctuations. And that can be tested experimentally. You can put the atoms in a cavity. Suppose you know the transition frequency. So you put the atom in a cavity where there are no eigenmodes of the electromagnetic field at that frequency. Right? You can arrange the boundary condition in such a way that there's no eigenmode of the electromagnetic field in that region. Then the atom will live for a very, very long time, in principle forever, if there was really no electromagnetic field at all in that frequency. It will live for a very, very long time. So that's a way to prove that decay of atoms is just measuring vacuum fluctuations. Okay. So as usual, I did very little compared with my program here, but that's okay. I think I prefer to explain in more detail. You have any questions?
Before you erase anything, we did a sum over all the final state that conserved the energy. But when
all the final states, the energy conservation comes through this integral dt. I remember I replaced this by integral dt. So that will force energy conservation.
Mm-hmm. Well, we still did a sum over all the final state, and yes. When we applied the sum over to the system, we only applied the sum to the system while there's still an F over the probe. Oh no, because we know the final state of the probe. That's
exactly,
why we didn't have.
Exactly. Yeah. Yes. Exactly.
Yeah. Oh, okay.
It's only the system we need to sum over, because the probe, we know everything. We know the initial state. We know the final state. We just set the particle. It's a certain energy, certain wave vector. It's in the vacuum. I mean, it can be light. It can be electrons. It can be neutron. Every time what comes here will be a little bit different, because this, will depend on the probe I'm using. Here I was using an atom that was decaying. You understand? But I know the initial state. For example, in the atom, it's in the initial state is some excited state, and the final state is the ground state. Okay, so I know everything here. But here, the best I can do is some thermal average and some overall final state that I don't know. So it's a very elegant idea. I mean, this is, this is equivalent, but it's just that it is simpler to think of it this way. And it's also simpler to do calculations this way. And you will see that when we go to response function, all that will happen is that instead of having this product here, so a measure of fluctuations in the system, what we will have is a commutator. And using the specific form of the density matrix, we'll be able to relate the linear response to the fluctuations. Okay. So that's it. If you want to stay and ask more questions, I'm available. But otherwise, we meet on Friday, and you keep getting